Foveated rendering leverages the limitations of spatial acuity and peripheral vision to allocate computational resources to the fovea while reducing quality in the periphery. Such methods are derived from studies on the spatial resolution of the human visual system and its ability to perceive blur in the periphery. However, the effects of blur on other visual cues that depend on luminance contrast, such as depth, remain largely unexplored. We present the first evaluation of stereoscopic depth perception for foveated rendering. We provide a perceptual model that models disparity thresholds for various blur intensities and eccentricities. For this, we designed a simple stereoscopic stimulus that serves as the basis for our psychophysical experiment. We measure it across various eccentricities and blur intensities. The stimulus is designed to match the peak sensitivity of the human visual system in all domains to obtain the lowest possible threshold. The ring is textured with a 50% random dot pattern that matches the peak sensitivity of the CSF. The width of the ring is adjusted accordingly and is set to 13 dots. This naturally leads to a slightly wider ring in the periphery. Furthermore, the ring exhibits sinusoidal depth corrugations. The number of corrugation cycles is tuned to be at the peak sensitivity per eccentricity as well. To mask the monoscopic cue of deformation, we dither the ring's edge randomly. The thresholds are estimated with a staircase procedure. The video shows an exemplary run. The amplitude of the depth corrugation is continuously adjusted based on the participant's performance. One complete session featured the judgment of 19 stimuli. The obtained data is processed as follows. We generate a data point for each measured disparity intensity such that the y-axis denotes the probability of detection. Afterwards, we bootstrap the data by repeatedly fitting a Weibull curve and estimating the 75% point. This procedure yields the final threshold as well as a weight per point. Estimations where the bootstrapping yields similar values have more weight in the final fit, as they are considered to match the real threshold precisely, whereas estimations that yield very different values are excluded from further evaluation. To create our perceptual model, we first fit a parabola to those weighted data points. Each parabola expresses different characteristics like steepness, upwards shift, and sideways shift. These characteristics are encoded in the 3 parameters of the fit. To complete our model, we interpolate between the parabolas by interpolating their characteristics exponentially. Our model shows that a certain degree of blur enhances stereo acuity. The acceptable level of blur increases with increasing eccentricity. We compare our retrieved blur values to common foveation intensities reported in literature. Our model demonstrates that these commonly used values do not harm stereo acuity. Finally, we validate our findings on 2 natural scenes. We modulate the overall scene depth in half of the image to determine the minimal amount of depth that is distinguishable from an image without disparity. They see both scenes in 2 rendering styles, a high-resolution image and a blurred version that is foveated according to our model. The results show that participants performed similarly for both rendering styles. They were equally as sensitive to overall scene depth in both scenarios. This shows that our level of foveation did not affect stereo acuity.